All right, in this video, we're going to look at Chapter 19, Section 5. We're going to talk about series and parallel circuits. We're going to start with the simpler of the two, and that is a series circuit. Now, in a series circuit, there is only one current path, and the current is the same in each part of the circuit. So let's look at a picture of a series circuit. Series circuit would have a battery or some other similar voltage device, and then we're going to add 1, 2, 3 resistors. There's the positive side of the battery. We're going to call this corner down here point B and this point A. So this voltage would be the voltage of A with respect to B. It might be 18 volts, it might be 12 volts. This is our first resistor. This is our second resistor. This is our third. You can see there's only one path for current to take. Current will flow. Naturally, positive conventional current will flow so that it's flowing in this picture clockwise. Current's leaving the battery at the positive terminal and current's entering the battery at the negative terminal. If we stop for a minute, we can think of the analogy that we've used before with gravity. Remember, a battery does work on charge, and in doing so, it gives the charge electric potential energy. It's very much like if we think in terms of gravity, picking a charge up at point B, or mass, and carrying it up to a height at A. Instead of 18 volts, we could think of something being carried up 18 meters. And then as it travels through the circuit, it naturally falls from high potential back to low potential. I always use the example of slides, like children climb up the ladder of a slide doing work against gravity, and then they naturally will slide down. If we think about it that way, you can see that the voltage gained as you travel through the battery should equal the same as the voltage that you drop as you go through all of the resistors. As you travel through the resistors, you lose potential. By the time you travel through the third resistor, you're back to zero potential. All right. If I want to find the voltage that I lose when I go through a resistor, I use Ohm's law, V equals I R. So this total voltage AB is simply the sum of the current times R1, that's the voltage across the first resistor, plus the current times R2, that's the voltage drop across the second, plus the current times R3. Now, in parallel, that current's the same, so we can actually factor that out. And then if I want, I can divide by I, and I get the voltage cos AB divided by I is simply R1 plus R2 plus R3. This voltage divided by the current, this total, that's the equivalent resistance. So R equivalent is simply the sum of R1 plus R2 plus R3. That's kind of intuitive. In series, if I want to find equivalent resistance, all I need to do is add up those individual resistors. Every time we add another resistor, if I were to come in and add another resistor, it would increase that total resistance. So let's put some numbers. Let's suppose that we have that picture and they tell us that the voltage across AB, our battery voltage, is 18 volts. Our three resistors are 1, we'll let that be 1 ohm. We'll let R2 be 2 ohms. And we'll let R3 be 3 ohms. So even though these are all three different resistances, because it is in series, we know that they will all have the same current flowing through them. You can't have current just building up in one resistor. It has to, the amount of current leaving one has to be the amount that's entering the other one. So they all have the same amount of current. Let's analyze this circuit, and we'll begin by finding the equivalent resistance. The equivalent resistance is just the sum, so 1 ohm plus 2 ohms plus 3 ohms gives us an equivalent resistance of 6 ohms. That seems pretty straightforward so far. Now that we know equivalent resistance, we can use Ohm's law. Remember Ohm's law, V equal IR, and we can solve for current. We know current has to equal voltage divided by resistance. And in this case, for this circuit, it's that battery voltage divided by the equivalent resistance. Those three resistors in series act like one big 6 ohm resistor. So 18 volts divided by 6 ohms tells us that the current through this particular circuit will be 3 amps. Now that we know what the current is, we can actually try and calculate the voltage drops, the individual drops for each resistor. Tell you what, let's work out, whoops, sorry about that. Okay, I'm having trouble getting it back to 100%. The voltage across the first resistor is simply going to be IR1. So 3 amps times 1 ohm is 3 volts. The second resistor, V2, of course, would be I times R2. Current is still 3 amps, but that was a 2 ohm resistor. So that gives us a 6 volt drop. And then V3, still 3 amps of current, but it was a 3 ohm resistor. That's 9 volts. If I add that up, 3 plus 6 plus 9, notice I get 18 volts. That's exactly what I would expect. These 3 voltage drops, those are like the slides that the charge is sliding down, have to total up to equal that battery voltage, also known as the voltage gain. That's going to be a really important idea in just a minute when we talk about Kirchhoff's rules, that as you go around a circuit, if you have a single loop or a closed loop, that the voltage gains plus the voltage drops have to be equal. All right, let's move on and let's look at a parallel circuit. Now, parallel circuits have more than one path. Since there's more than one path that current can flow through, the current does not have to be the same in each part, and very likely won't be the same in each part. But in parallel, all resistors have the same voltage across them. I'm going to draw a parallel circuit 2 different ways. One way so that you can really see what's going on, and then another way that's a little more neat and tidy once we understand what's going on. So suppose we have that battery still. Here it is, voltage. Here's the low or the ground. There's point B. Here's point A. So there's our voltage supply. And I come in and I just connect one resistor. One resistor in a battery is the simplest one I could possibly have. There it is, R1. R1, if this is a 18-volt battery, then R1 has 18 volts acting on it. You climb up through the battery and you gain 18 volts. You slide through R1 and you lose 18 volts. But what if I connected another resistor right here? Here it is. It's kind of messy looking, but there's R2. Notice that R2 has this exact same potential difference across it, the same voltage. If you start at point B and you go up and you gain, you can slide down R2, okay? In this case, remember, the charge will have to choose. It can go through R1 or it can go through R2, but it can't go through both. It's just like if you have 2 different water hoses connected to the same water supply. Some of the water will go through hose number 1 and some of the water will go through hose number 2. But if they're both connected at this point A, they can't go through both. So you go through the battery and gain 18 volts of potential, and then it can go through R1 and lose 18 volts of potential, or it can go through R2 and lose 18 volts. If we wanted to, we can add another one over here. We call it R3. Again, R3 has the same voltage gain. So we really have 1, 2, 3 different current paths, and each of those current paths have the same voltage across them. But this isn't how we normally would draw that. So I'm going to draw it again, only now I'm going to make it a little neater and a little more traditional. So there's our first resistor. We normally just draw it side by side. There's R2. Here's R3. Now remember, we said that wiring has minimal or negligible resistance. So essentially, if this is a 12-volt battery, just pick a number, and this is at 0 volts down here at point B, then this is at 12 volts. Every point up here, this point, and this point, and this point, and this point, any point I could pick along here is at 12 volts. Okay, if we want to use our analogy, it's like if we climbed up from 0 to 12 volts or 0 to 12 meters and we're standing up on a 12-meter platform and we have our choice. We can slide down chute number 1 or slide number 1. We can slide down slide number 2, or we can slide down slide number 3. We can't do all 3 at once. When we slide down, we will be back at 0 potential because every point along this point down here, those are all 0 potential points. It doesn't matter. Okay. Let's take off the number for right now. We could probably not have all those little dots, but I'm not trying to erase those. All right, so in parallel, the voltage across them all is the same. So the voltage across AB is equal to the voltage across the first resistor, which is equal to the voltage across the second resistor, which is equal to the voltage across the third resistor. Now, the total current leaving the battery has to equal the current that flows through the first resistor. So I'm going to say, look, there's some current's going to go down here. We call that I1. More current's going to flow down here. That's going to be I2. And there'll be even more current here going through I3. If I want to know how much current leaves the battery, it's the sum of all of those. That's my total current. I don't know how much it is, but you can picture. Here's the total current. Leaves the battery. It's going this way. When it gets to this junction, some of that current will flow through I1, and some of that current will continue this way. When it reaches this junction, some of that current will flow through I2, and some of it will continue on this way. That's I3. When it gets back here, you can see you're going to have I2 coming in, you're going to have I3 coming in, and they're going to add up together, and they're going to go this way. And when you get here, you're going to have I1 coming in. It's going to add up with I2 and I3, and the total current will head back into the battery. So the total current is the sum of the currents through the 3 resistors. To get equivalent resistance, I use the fact that the voltage divided by the total current, I'm going to say that differently. Actually, I'm going to say it exactly that way. That the current is equal to voltage divided by resistance. So the total current is equal to the voltage across AB divided by the equivalent resistance. The current through I1 is the voltage across AB. Remember, they have the same voltage, divided by R1. The current through the second resistor is the voltage across divided by R2. And the third one is that circuit voltage, AB, divided by R3. Remember, the voltage is the same. All of these voltages are exactly the same, so I can divide those out. And I see that in parallel, 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. If there's more resistors, you just keep putting them like that. That formula looks really, really similar to the formula we had for equivalent capacitance in series. I don't know if you remember that. All right, let's see if we can solve a problem with some numbers. We're going to let that voltage be 18 volts. I'm going to let R1 be 1 ohm. But this time R2 is going to be 3 ohms. And R3 is going to be 6 ohms. Let's find equivalent resistance as our first step. 1 over equivalent resistance is 1 over 1 plus 1 over 3 plus 1 over 6. If I put that in a calculator, I get 1, the whole thing comes out to be exactly 1.5. Now that's not the equivalent resistance. Remember, this is 1 over. I'm going to need to do, to get the equivalent resistance, I need the reciprocal of that. It's 1 over 1.5. Or I need to use that 1.5 to the negative 1 on my calculator. And when I do that, my calculator gives me this. All the way out there till it runs out of spaces. If I only have 2 significant digits, I'm going to just round that to 0.67. You know, if you're comfortable with fractions, you might want to write this. And the only problem is fractions imply exactness, and we're never exact in physics. So we work with decimals normally. So there's the equivalent resistance. If we want to look at the current, that's going to really tell us if we did things right. Let's look at the current for each branch and the total current. If I use equivalent resistance, the current is equal to the voltage divided by the resistance. So to get that total current, that would be the 18 volts, the voltage across AB, divided by the equivalent resistance. It would be 18 volts. I can use that 2/3 here. It's not a final answer. And when I do 18 divided by 2/3, I get 27 amps. That's the total current leaving the battery or through the battery, because it also enters it. I can check that by just seeing, you know, what's the current through each branch? That's easy to do. If I want the current through each branch, the current through the first branch is the voltage divided by R1. That's going to be 18. R1 was 1 ohm. 1 ohm. So I get 18 amps for the first one. If I do the second one, it's 18 volts divided by 3 ohms. That's 6 amps. Notice as we increase the resistance, we have less current flow. And then the third one has the most resistance, so 18 volts divided by 6 ohms is 3 amps. If I add those up, 18 plus 6 plus 3, I get 27 amps. That makes sense. One of the things I really like about working with circuits is when you've got them done correctly, all of the numbers make sense and you can kind of check things. Let's look at a combination. Unfortunately, most real life things are not going to be simple series or simple parallel. Most of the time, what we end up with is some type of combination. So let's look at a series parallel combination. And I'm going to draw it differently just because I want you to get used to the idea that everything doesn't have to look the same every time. So I'm going to start with a battery. And it goes this way. And there's a resistor. And then all of a sudden it branches out. There's going to be 2 current paths. There's another resistor. Here's another resistor. And then they go back together. And there's my circuit. This is the positive side of the battery. That's the negative. That tells me that current flows this way. In the battery, current flows from low to high potential. And then, of course, in the circuit, it continues on around, trying to get from high potential back to low potential. They tell me that R1 is 6 ohms. So are R2 and R3. They're all 6 ohms. So R2 is 6 ohms. R3, 6 ohms. Our battery, here our EMF, is 18 volts, a very popular choice today, and the internal resistance is 0. We haven't done anything with internal resistance yet, but we will. All right, the question wants us to just analyze this circuit, find the total current, find the current through each branch, find the voltage drops. We just want to find everything we can possibly find. The first thing I would find is equivalent resistance. And the first thing you need to do to find equivalent resistance is look at the pair that are in parallel here. If I take these two, they are in parallel. I know they're in parallel because this point and this point would be a potential difference. If you go from here through R2, the potential difference is the same as if you go from here to R3. There's 2 paths. So for that little purple part, the equivalent resistance would be 1 over 6 plus 1 over 6 is 2 over 6. When I take that reciprocal, I get 3 ohms. Anytime you wire 2 identical resistors in parallel, the equivalent is half the amount. So a 10 ohm and a 10 ohm in parallel will have a total of 5 ohm resistance. Or, I don't know, an 18 ohm and an 18 ohm in parallel will have a total of 9 ohms resistance. So this could be acts like a 3 ohm resistor. If I redrew this picture where I had the same battery, I would now have a situation where it's equivalent to R1, which is 6 ohms, and R equivalent, which is 3 ohms. It's just like you could replace those two resistors, and as far as the battery or the circuit's concerned, they act like a 3 ohm resistance. It makes sense that it's less because if you have two current paths for current to flow through, it's easier for the current to flow. This was 18 volts. That's our EMF. And it doesn't have any internal resistance. That's an ideal. All right, so now that we've replaced that, we now can look at a different equivalent resistance. We could look at these two. Those two clearly are not in parallel, they're in series because you have to go through one and then through another. So for those two, their equivalent resistance would simply be 6 ohms plus 3 ohms equal 9 ohms. That's the equivalent for the total circuit. Our total circuit has an equivalent resistance of 9 ohms. If I want to go now and get current, I know I can use V equal IR. I have 18 volts. I don't know the current, but I do know the resistance is 9. I'm going to get that the total current in that circuit is 2 amps. Let's look at voltage drops. To look at voltage drops, we really need to look at that top picture again. When the current goes through the battery, every coulomb of charge gains 18 volts of potential. If we do the voltage for R1, it's the current through R1 times the resistance of R1. Well, how much current's flowing through R1? Well, it's going to be the same as the current in the battery. This is the battery current, or the total current. But you can see the current that leaves the battery enters R1 because R1 is in series with the battery. So the voltage across R1 is 2 amps times 6 ohms is 12 volts. Remember, there's an 18 volt battery. I'm going to do the current voltages in green. What we just determined is from here to here, if I go across from here to here, there's a 12 volt drop. If I go across the battery, there's an 18 volt gain. That tells me that this has to be right here a 6 volt drop because it has to be a total drop of 18 volts. Let's use some common sense. If I have 2 amps of current flowing out of the battery, flowing through R1, when it reaches this junction, if these two resistors are equal, it makes perfect sense that that 2 amp current's going to divide, and you're basically going to have 1 amp that goes through R2 up here, and 1 amp flowing through R3. I put I really should have put an R. I mean a 1. So 1 amp. That 2 amps of current just splits in half. If we look at the voltage drops, it's going to be I2, R2. If there's exactly 1 amp of current flowing through it, and it's a 6 ohm resistor, that is a 6 volt drop. That makes perfect sense. That's what we said it needed to be. Obviously, since they're in parallel, when we look at R3, it has an identical 1 amp current, an identical 6 ohm resistor, so it too equals a 6 volt drop. Okay, I think that's enough. I want to do maybe just a little more practice on equivalent resistance, so I'm going to just look in the book quickly. We'll make up a problem, or we'll steal one of their problems, and we'll consider how do we get equivalent resistance. This is problem 40, number C. It's got a whole bunch of resistors. We're not going to do every part, we'll just do C. It starts with one little resistor like this, and then it subdivides. And it says there's a resistor here, and there's 2 resistors in here, and there's 1 resistor in this branch. We've got 3 different branches, and all of a sudden all these branches come back together again. And then they branch out again. There's a resistor. Here's a resistor. And finally, 1 more resistor. Okay. Generally, my approach on things like this is you want to work, and I don't know a better way to say this than from the inside out. We just have to start simplifying. The most inner sort of tract we might see would be to start right here. Oh, I don't have the numbers on it. We definitely need the numbers. So let's see. We have 19, 32, 13 and 15, 14, 72 and 45, and the very last one here is 24 ohms. So just a whole bunch of resistors. I would start by looking at the 2 right here in the middle. Those 2 are in series with one another. Current has to flow through the 13 and then flow through the 15. They can be replaced, and they'll be replaced by 1 28 ohm resistor. In series, we simply have to add. So I can erase right here and just say 13 plus 15 . A 13 plus a 15 in series is the same as having a 28. All right, easy enough. Now let's say, hey, what about these 3? These 3 are in series. In parallel. They are side by side. They all have the same potential drop from here to here. Whatever that is, that's whether you go through the top or whether you go through the middle or whether you go through the bottom, they're in parallel. So for those, I would say, look, I got to use this rule. 1 over 32, 1 over 28, 1 over 14. I get an answer. 1 over 32 plus 1 over 28 plus 1 over 14. I get this terrible little decimal number on my calculator, 0.138, blah, blah, blah. I'm just going to use that -1 button, that inverse button, and I get that the equivalent resistance is 7.226. That's too many significant digits, but I'll do my rounding later. That means I can erase all of that. All of this could be replaced by one resistor. And that resistor has 7.226 ohms of resistance. I need to do something very similar with these two. They're also, as you can see, in parallel, side by side. 1 over 72 plus 1 over 45. 1 divided by 72. The one thing I know is the total resistance in parallel is always less than the smallest resistor. So this answer is going to be less than 45. This part came out to be 0.361 repeating. And then when I take the reciprocal, I get 27.69. That basically means I could erase this. And I can now put in another resistor that's 27.69. If I want to get the equivalent resistance for the whole thing, those 4 resistors would now be in parallel. It'd be 19 ohms plus 7.226 plus 27.69 plus 24. Notice, precision-wise, I have to end up at the nearest whole number. That's my least precise place. I just wanted to carry along this because notice this 226 plus that 0.69, that's going to add another ohm to our total answer. 19 plus 7.226 plus 27.69 plus 24 comes out to be 77.916. So my answer when I'm done is 78 ohms. All of those resistors that we started with allow charge to flow from that battery as if it was a 78 ohm resistor. All right, that's the end of this video.